Okay, so welcome everyone. This is the last lecture of the preschool of Christian on CFT basics. Okay, please start, Christian.
It's not the last, it's the second to last. Right? Tomorrow there's one more.
Oops, sorry.
No worries, no worries. Yes, thank you, Saskia. Welcome everybody, welcome back. I have a minor comment. So today I'm going to deviate from the main path outlined in the notes a bit. I'm not going to deviate, but I'm gonna take a shortcut. As I said in the first lecture, it's impossible for me to cover everything that I typed down. The notes are just a more complete version of these recorded lectures, and they're for your personal use, so that you can go find much more detail, all of the details that I'm presenting here and many more online. So before I start, since also for tomorrow, I won't be able to cover everything. So what I have decided is today I'm going to do a bit more of a safari style lecture. So I'm going to guide you through the concept of a primary field and how it results in a state called a primary state, with the ultimate aim of explaining to you the concept of fusion. And I'm not sure I'm going to reach that point today. Maybe I will. We're going to reach it tomorrow. But anyways, for those of you who have found time, say operator product expansions, or well, if there's any of these, just let me know. With that out of the way, let's just recap what we did last week. So we looked at generators of conformal symmetry, and we discovered, so starting from the notion that conformal transformations are essentially holomorphic functions and anti-holomorphic functions, we wrote down just an infinitesimal holomorphic function, which is this one here. And we proceeded and wrote down generators for these things. First of all, we looked at the global conformal group. We wrote down generators for holomorphic functions and made the notion of a global transformation, a global conformal transformation, more precise in the sense that it is well defined everywhere in the sphere. And then we also made the notion of local conformal transformations precise in the sense that they are not defined well defined everywhere on the sphere. The sphere being the Riemann sphere, like the complex plane with one point at infinity included. Those are the local ones. Then there was this exercise that I encourage you to do. I hope you did that. It's not a difficult one. That's the Witt algebra. This is the classical conformal symmetry algebra. And then I argued that in the quantized version, this algebra is being deformed. There's sort of a quantum correction, and that's the central extension. The central extension, central means in the math literature, it commutes with everything. And physically, this term is essentially an anomaly. Okay, we discussed that. And then we talked a bit about the energy momentum tensor and came to the conclusion. The first important conclusion is that the energy momentum tensor, where is it? Is traceless. Here we go. This piece here, the energy momentum tensor is traceless. This is a hallmark of a CFT. And restricting to 2 dimensions, the tracelessness is for any dimension, and restricting to 2 dimensions, we were able to write down the 2 independent components of the energy momentum tensor, and we found by using conformal symmetry that these 2 independent components are, one of them is just holomorphic, the other one is just anti-holomorphic. All right. And then we came to the concept of fields in a CFT. We decided that we would, so we have four types of generators: translations, rotations, dilations, and special conformal transformations. And we decided, so we saw that we can, so in 2 dimensions at least, well, actually in all dimensions, but we looked at 2 dimensions, we can actually have two commuting observed operators, which are L0 and L0 bar. And we like to use these two operators to classify to provide quantum numbers for our states. And so that's what we're going to do. And these eigenvalues are called H and H bar. And that gives us the notion of a scaling field. Or basically these are called conformal weights because under just a scaling, so a dilation of the space-time, these things just pick up a scaling factor. That's just this lambda, and this lambda is basically is exponentiated by the power of the scaling weight. Okay, and that handed us eventually the notion of a primary field, which behaves like a scaling field for pretty much not pretty much, for any conformal transformation. That's what it does. So this is the primary field, and these things are the center of our attention, pretty much in CFT, together with the energy momentum tensor. In the sense, the energy momentum tensor prescribes the symmetry, and these primary fields are going to be the representations. That means the fundamental blocks of a model that we will be juggling with, and the concept of fusion that I hope to describe at the end of this lecture or tomorrow is going to make that a bit clearer. Okay. Then there's this notion of a quasi-primary, which just means that it's only behaving like that for a global conformal transformation. But for now, it's not so important. For now, let's just focus on the notion of a primary. Okay, so far so good. So that's a small recap. Do you have any questions?
Maybe it will become clearer during the lecture today, but what do you mean if you say that physically the central extension is an anomaly?
What do I mean physically? You mean as in an experiment, or you mean in comparison to other anomalies?
No, I mean, what do you think of when using the term anomaly?
Oh, what does it mean?
Yes.
Okay, good. Thank you for the question. So let's make it. Let's start writing. So in quantum field theory, when we speak of an anomaly, we mean the following. So you have an action which has a symmetry. So let's say an action of a field phi, and then it has a symmetry. So that means you can take phi and modify it by some symmetry action, which is this delta phi. And if this action is essentially the same, then we speak of a symmetry, right? Hold on, I keep forgetting it. Up to total derivative is for the Lagrangian, I believe. The symmetry needs to be the same here. So the point is, this can be messed up quantum mechanically. Quantum mechanically, what you actually want to do. So quantum mechanically, you're interested in something called the partition function, which we write usually. This is called a path integral. I don't know, this is going to be schematic if you're not an expert with quantum field theory, but the idea, I'm going to try to explain the idea nevertheless. So this is for a Euclidean quantum field theory. That's why there's an I. Let's make this an I. This is not a standard quantum field theory, not Euclidean. So this thing here, here's the action. And if you implement, so you start with a system which has a symmetry classically. So this thing here will have the symmetry. So this is symmetric by virtue of by demand, sort of by assumption. But what can go wrong is that now quantum mechanically, you also have to transform this measure. And this measure can transform. So there is, so to say, let's call this phi prime. This measure need not necessarily be the same. So that means that let me be a bit more precise here. Here's well, this is not good notation. Let's call it Z. That means that the partition function under symmetry transformation can transform. It can pick up an additional piece, and if that happens, then we have clearly found that quantum mechanically, a symmetry that is present in the classical theory is not present in its quantized version, and then we speak of an anomaly. And this is usually manifested in stuff like, for instance, quantum classically, we have a conserved current, something like this. And then quantum mechanically, you would like to look at the 1-point function. So the current is going to be promoted to an operator. That's why you need the 1-point function. And if the symmetry is preserved in the quantum version, then you find this. But if there is an anomaly, you can find something non-vanishing. So that's what an anomaly is. Did that help? All right. Okay. Are there other questions? Okay, then let's get started. Let me copy. I'm going to copy this here. Copy. So, okay, so this is the notion of a primary field. So this is primary. This is the notion of the primary field, and we observe that there is one field amongst these. One field. There's a field with h equals h bar equals 0, which is inert. Under conformal transformations, which is inert under conformal transformations. Okay, so this field is called the identity field. And I'm going to denote it by a 1. This is supposed to be a 1, like a math BB 1 in LaTeX. So this field is constant in space time, sort of. It does not depend on Z or Z bar. And as such, it also doesn't really pick up any of these transformations. It's completely ignorant to these transformations. Like, it doesn't care. And this field is going to be special. We're going to see that in a minute. And we're going to assume that this field is unique. Assume that the identity field is unique. Okay, that's just a small detail. For now, you need not worry why this is the case. And all other fields, so I should point out, this is a primary field. So identity, hold on, there is primary field. Let's call this a primary field. Sorry, I hope you haven't copied too much. There is a primary field. So in all other fields, all non-primary fields are called descendants. I think that's within A. Okay. I'm going to be a bit more precise about descendants. So in the notes, I'm a bit more precise about descendants already at this point. But for now, since I wanted to take a shortcut, I will be more precise later on in this lecture when we discuss the connection with states. Okay, so this is a descendant field. And for you as an exercise, to get an idea, so there is an exercise 4.2 where you take free, massless, and real bosons and fermions. They have an action which in complex coordinates, the boson looks as follows. Del phi, del bar phi. Okay. And the fermion, that fermion has an action which looks like this in complex coordinates. Psi bar del psi bar plus psi del bar psi. And so there is a Dirac. So these are basically my Majorana spinners. These are components of a Dirac spinner, which is this thing, psi of z and z bar, psi bar, z bar, z bar. Okay, so then what you're supposed to do is derive the equations of motion. Equations of motion. And from that you find a relation for, you find a dependence for, say, del phi as a function of I'm going to spoil a bit. For instance, as a function of z, you don't have to solve the equations of motion. You just need to sort of realize that so is del phi either a function of z or is it a function of z bar? And with that, just take a conformal transformation. Conformal transformation, z and z bar goes to fz and fz bar, and derive, and assume that del phi is a primary, and derive h, comma h by varying the action, well, by transforming the action. And then likewise for the fermions. Likewise for psi and psi bar. In the notes, I'm a bit more clear on the exercise. Maybe here I'm being a bit sloppy. The point is that you're going to find the conformal weights. So the point is to find the conformal weights for the fields del phi, del bar phi, psi, and psi bar. That's sort of what you're expected to do. Okay. Now, in the next step, let's look at correlators. So these are going to be just very, very minimalistic account on correlators. That's why I call it a few words. A few words on correlators and the operator product expansion. This is a long title. I have to admit, though, that I won't talk here for time reasons. I won't talk about the operator product expansion. So for the lecture, this is actually going to be in parentheses. Actually, let's put this here. Okay, so basically, what do we care about correlators? Well, fields sort of communicate. Like on the lattice 2, fields communicate with each other in correlation functions. So these are an integral component of any physical theory. And we should take a look. And here I'm going to sketch. So in the notes, again, I am complete. Like I said, today is a bit of a safari. Here I'm going to sketch how you can do two-point functions. Two-point functions in CFT. In CFT. And I'm going to restrict to the holomorphic sector. Sector. And the anti-holomorphic sector, is the same. Analogous. So, okay, so what we want is we're interested in the following correlator. I'm going to call it G, and it's the two-point function of a field phi1 of Z and a field phi2 evaluated at W. And this is the thing that we're interested in. So this is what we want to compute. And now we're going to see a little bit of conformal symmetry in action. So, for instance, the first thing is that invariance under translations. So invariance under translations, so that's a function f of z is just z plus a shift. Well, this is something that you've most likely already seen in a standard QFT class. What it means that this function be independent of such a shift, it really just demands that the function g of z comma w is truly a function only of the difference between of z and w. Otherwise, otherwise the translation invariance couldn't be satisfied. Now something new, invariance under dilations. Invariance under dilations, that's a function of this type, lambda z. So let's take a look. Let's see how that goes. So we have this function phi1 of z, phi2 of w, and we perform a dilation. And we're going to assume, I should say that. So these two, let's assume they're primary. So now we're using the primarity of these operators. And we're using the transformation that I copied in the beginning. And what this means for this transformation is really just this phi 2 lambda w. So this is just the transformation property, and we can just factor these things out, and what we get is this relation. And invariance is now the statement that this is the same as doing nothing, right? And you can convince yourself that what you find, so that the following expression is a solution to this constraint, or is the solution, I should say. There's going to be a constant, which I call d12, and a power law of this type. And so sort of this is how we see that scaling transformations, how they impose a constraint on a two-point function, right? The third thing that I won't display here is invariance under inversions. Instead of taking special conformal transformations, it's usually more direct to just take inversions, which means f of z is, the minus sign is just cosmetics. And in the notes, I carry out how you would proceed. And from here, you find the important constraint that this is sort of that invariance under inversion can only be satisfied if and only if the conformal weights of the two contributing fields are indeed the same. Okay. So in conclusion, we find for a two-point function, we find for a two-point function that d12 is the following 2h1, and here there is importantly a delta. And similarly, we can repeat the same thing for antiholomorphic fields. To C bar, and we will find some other constant potentially, but usually it's just all of these constants are set to 1. And all that we find is a bar on top of everything. Okay. So there are some remarks that we can do. Or actually, so this is an important result. So this is the two-point functions. The two-point functions of in conformal field theory are really completely fixed by conformal symmetry. So that's up to one constant. And this constant here is going to be the normalization. So these things, if I normalize the fields in a particular way, I can just get rid of these d12. So these are just normalizations of fields, which I'm going to keep them around, but in practice, these are usually just set to 1. Okay, some remarks. First remark, we're going to see this in a bit. Delta 1, 2, this contribution means that phi 1 and phi 2 are orthogonal in a way that it's going to be made more precise in a minute. Once we talk about states. See below. Then if we fix phi 2, say, of z to be the identity, meaning h2 is 0, then we find from this sort of the 2-point function becomes a 1-point function because the identity field is the field that does nothing. So we find from this that phi z, I'm dropping the 1 now, is basically delta h comma 0. Well, we could have this d what do I call this, phi 1, but this here is usually set to 1. And this is an important result. The important result is that in a CFT, by conformal symmetry, fields cannot have a 1-point function except when their conformal weight is 1. So that's this delta function here. Sorry, when their conformal weight is 0. When their conformal weight is 0, it can have a non-vanishing 1-point function. And that means it needs to be the identity field, since we assume that there's just one unique field which has conformal dimensions h and h bar being 0. But here I'm restricting to just 1/2, like the holomorphic half. Okay, so there is a power law decay. And this is how, sort of traditionally, if you will, conformal symmetry is detected in experiments. In a power law decay, as opposed to exponential decay. That here, if z and w are being moved far apart, you have a characteristic exponential decay. Okay. All right.
Excuse me?
Yes.
I think we couldn't hear you for a moment. Could you repeat what you said last?
Oh, okay. When did I black out? I guess, okay, I'm just gonna start talking here. So the 1-point function, the crucial point is that the only field which is allowed to have a non-vanishing 1-point function, expectation value of its own, is the identity field, which has conformal dimension 0. That's the first point. The second point that I made is that there is a power law decay. So when correlators, so you look at this correlator, and you have z and w be further and further apart, then this thing is going to be decaying, and it's going to be decaying with a power law. And this is a smoking gun of a CFT. If on the other hand, there is a scale like a mass in the theory, usually you have something like an exponential decay. Okay, so these are the things that I said. I hope I didn't black out for longer.
Hi, can I ask a question?
Yes, please.
And maybe I'm confusing things, but we did not check for the correlation functions invariance under rotations, right? Should that not further constrain, like z minus w becomes like the absolute value, or is that?
Thank you. This is the next comment.
Okay.
There is under rotations, what we would find. Here's the thing where actually I have to be a bit more concrete. So far I restricted to only the holomorphic or only the anti-holomorphic sector. And rotations will indeed, what it will do is will force you to have dependence on, let me just make a sketch here, on z minus w bar. So this thing is invariant under complex rotations, which are multiplications by phases, right?
Yeah.
Okay, so what you will have in like when you have a CFT, it's always going to be partnered with a holomorphic part is going to be partnered with an anti-holomorphic part. So what you really have is this here. You really have this here. And the requirement of rotational invariance basically tells you that you should, in the end, always combine. If you have a physical thing, you should combine. You should combine your expressions, and what you will have is h1 comma h2 z minus w to h1, and then the same for the anti-holomorphic sector, h1 comma h2, they both have a bar, z bar minus z bar to h1 bar. And you see, at least, okay, now one has to be a bit more careful. For instance, if h1 and so usually, now it depends on the representation of the field. If they are spinless, so if they have S, that's H minus H bar when they're spinless, then you see that basically what this becomes is, or what it contains is this piece here, 4H1. Where now, sort of by virtue of this, you have H equals H bar. And you'll sort of see these expressions popping up. So this is the requirement of rotational invariance here. Okay.
Is D12 a real valued parameter?
Excuse me? Is there a real value?
Is D12 a real valued parameter?
It need not be. It depends on, so there are examples where you can define. So okay, let's put it this way. At the end, what you can I think I blacked out again. Is that true?
Yes.
Okay, let me start over. What wants to be real is this 2-point function. The operators themselves can be imaginary, and if the operators are imaginary, then you need to choose these normalizations such that the 2-point function is going to be real. If the operators actually give our observables. Oh, actually, sorry. Turn that around. Well, let's be more concrete. So observables, we're looking for correlators of observables, which are typically real, right? In the sense that they are Hermitian. So I'm having in mind an example where you can have sort of a free boson, and you can have this here as an operator. Let's call this J. And then you need to choose these things here appropriately, such that the 2-point function of J is real. Actually, I think actually this I here, I'm a bit shaky here because I have done this example a long time ago, but this I basically ensures that, so that's this normalization here, D12, and it ensures that the correlator is real. So that's sort of the idea. Bottom line is, if by 1, 2 are observables, sort of, or fields that lead to something observable, this thing wants to be real, and then these are going to be typically, they're typically going to be real. Actually, let's just leave it like that. But I wouldn't be surprised if there are examples where one throws in an I or something like that. For most purposes, for us, they're just going to be 1. Okay,
Sorry, I
yeah.
just wanted to clarify something. So here down there, when you wrote, so h is equal to h bar, and then it becomes indeed just a function of the absolute value. And but this is after you change z bar to the complex conjugate. So
Yes, yes.
okay. So we complexified z and w, but at the end, if you want to say the physical surface, then you have to change them to the.
Yeah, right. At the end, like if you hand this to your favorite experimentalist, right?
Mhm.
You need to make sure that you've reverted to the physical surface, meaning that z bar is indeed the complex conjugate of z.
Okay, but the demand that it's invariant under rotations is only on the physical surface.
Well, here I used it only on the physical surface. It should be, I actually haven't checked. I can check if rotational invariance, let's see.
Because if it has to hold
We have
always, then I would think that it always has to depend on the absolute value. That's why I'm confused.
let me actually turn it around. Actually, we have implicitly, sorry, I have overlooked one thing. Remember that, let me pick a different color. This thing here, remember that a rotation is going to be just multiplication by e to the I phi. And a dilation and a rotation, remember the statement that I made some point where I said I can take z to be r times e to the I phi. This is a real dilation, but I can also take,
Sure.
oops, rz, or this thing, right? So, and lambda is just the product of the two. So rotational invariance, so sorry, I made a mistake. I
Oh, yeah, I see.
was sloppy. Rotational variance is actually already included in here.
I see. Yeah.
Scaling
Makes
by a
sense.
complex number.
Yeah. Thank
And
you.
but this other statement here is still nevertheless true. Hold on, then I need to actually correct what I said. It is kind of rotation invariance, but it's more the statement here. It's more the statement that at the end of the day, a correlator should be a real number if it's physical. If it's something complex, then you probably messed up. Okay. All right. Thanks for the question. So now the next thing, let's see, I need to speed up a little bit. So I'm just going to sketch an exercise. 4.3. Go look at the notes for a better text, so to say. 2-point functions in the Ising model. Functions in actually for free fields. So this is exercise 4.3, and there's exercise 4.4, which is very, very simple. So association of Ising model with a CFT. So in the Ising model, what you find is that you have correlators of something called the energy operator. So let's declare lattice sites. Site. So this is site n, and then there is site 0, obviously. And this thing, you can just evaluate that on a lattice, and you will find 1 over the distance squared. And similarly, there's a spin operator where you can do the same thing. And you will also find the power law. But this power law is going to be 1 over 4. And there exists a CFT. So now what I'm asking you is sort of to find CFT fields. Or find CFT, fields. Oops, fields with H bar such that they match these correlators. So this is a very simple exercise. Once you have I just want you to think a bit about 2-point functions. That's it. It's not a Herculean task. And now there's something that, unfortunately, this is something I have to skip, because it's not going to be super duper important for the outline of what I want to convey in the main part in next week in the lecture. But it is nevertheless a very, very crucial concept in CFT. So if you're interested in CFT, read the notes on operator product expansion. So what is the idea? The idea that one has here is that sort of I have a field phi1 and I have a field phi2 and I have them bump into each other. Sort of, I'm going to indicate this by arrows, and a new field comes out, but it's actually going to be a collection of fields. It's like sort of a little collision experiment, like a scattering experiment. And there's a bunch of new fields that pops out of this, and it's going to be a sum over fields K. And this thing here is sort of the interaction strength. And it appears sort of if I take phi1, phi2, and phi k, and I take a correlator, then C1 2k. Let's make this proportional. C1 2k will appear here. So this is an important concept which I will skip here, because it leads a bit off track from leading to the fusion rules. But as I said, so maybe there's time in the end and I will discuss this a bit. Though, I mean, I'm already 50 minutes in. Let's see. I doubt it a bit. Okay, so the next thing that we want to talk about is to see that I don't black this out completely. All right, the next thing is 4.3 radial quantization. Oops. Quantization. And the aim here, is that in CFT, there is a correspondence between fields. To any field phi, I can associate a state. A state, I'm going to call this ket phi, which lives in Hilbert space. And today, so now we're going to slowly inch in toward more of a quantum description in the sense of a Fock space. Okay, so how do I understand this? So how do I make this notion a bit more precise? So to understand this, we move to the cylinder. From C, that's the complex plane, to the cylinder. And a cylinder is one non-compact coordinate times a compact coordinate. And how do we do this? We take the complex plane, and I use Z as coordinate for that. And now W is going to be a coordinate on the cylinder. And W is going to have a real deciphering, or what's real decoding, I think it's called, tau plus I sigma. So tau is in R, and sigma is in 0 to pi. So tau is the real coordinate, evidently, and sigma is the coordinate on S1. And let's draw a picture. So for W, for W, so we have the cylinder. So tau runs upward. sigma runs in the circle, and this is going to be mapped by this exponential mapping onto the complex plane. And how is this mapping? The mapping goes as follows. Let me draw. So if I take a constant time slice on the cylinder, that's one circle like this. And what this is going to be, it really is just going to be a circle. So sorry, here's the origin, and the circle is just going to be somewhere like a concentric circle about the origin. Let's call it that. And then I can take another circle, another constant time slice at later time. And this thing is really just going to be a bigger circle. So what we're observing here is that time on the cylinder, which flows upward, flows outward radially. Actually, let's make this a bit bigger. It flows outward radially, and it's basically e to the tau. And similarly, sigma, let's make this outside, e to the I sigma is sort of the motion on the circle is just the motion on a concentric circle on the complex plane. The motion, so on the cylinder, the motion on the S1 is a concentric circle. Is that sort of clear? So in this way, you can take a cylinder and you can explode it onto the complex plane and vice versa, right? You can undo that. So this is log z, and z is e to the w. Okay. Okay, so temporal evolution. So temporal evolution. So there's a remark here, temporal evolution. Our scalings are real scalings. There was an exercise. So exercise, what is it? 3.3 that by now there's a solution to it in the notes. So we had z goes to rz, which is e to the tau z. And this is generated by generated by L0 plus L0 bar. And this is sort of what we see here. So we see that if time is being evolved by, let me nail this. So usually the Hamiltonian is responsible for temporal evolution. And here we see that what is responsible for temporal evolution is L plus L0 bar. So we declare this thing here to be the Hamiltonian, right? So L plus L0 bar is the Hamiltonian, and that's the thing that sort of is responsible also for dilation. So this is a statement in CFT that the Hamiltonian is the dilation operator for real dilations. As we pointed out just now, if you take complex dilations, you can also have the rotation included. But recall that the rotation is the one with the opposite sign. Let's just get rid of here because it will be confusing. And then another comment is that QFTs. Let me turn off my. It's annoying. There you go. Another comment is that QFTs are quantized with respect to constant time slices. That means that states are associated with constant time slices. We're going to talk about one particular time slice in a bit. But this here, because constant time slices are radial, they're concentric circles lying at a radial distance from the origin. This concept here, or this setup is called radial quantization. Jesus Christ, my handwriting is terrible. Quantization. Okay. So now that I've hinted already at states and so on, let's talk about states. Time is it? Okay. So let's talk about asymptotic in states. So there are going to be some assumptions. So there exists. So the first one is existence of vacuum state. In the sense like that we do it in free field theories where you have, say, a Fock space and there is no momentum mode sort of acting on this ground state. So it's the state of zero momentum or whatever quantum number you have in mind. So this is actually, let's make this 1. 2, we're going to assume that the structure of Hilbert space is the same for free and interacting CFTs, but the eigenstates may be different. Eigenstates are allowed to be different. This is just a minor remark for now.
What are you referring to as structure?
We're going to see this in a like, I hope I'll get to this. So I'm going to construct a Fock space, if you will, in a minute. Well, not in a minute, like in 20 minutes, I hope. I'm going to construct a Fock space. And you're going to, so at that point, you won't be able to tell the difference between a free theory and an interacting theory. So it's really going to look the same, but the difference is going to be that the ground states are allowed to be different. So that's what it means that the eigenstates are different. You're going to see. Let's see below. Let's make a comment. See below. Yeah, I understand it's sort of a cryptic comment, but maybe I should have pointed it out in the moment where I do talk about states. So, and then interactions fall off at infinity. At tau goes to plus minus infinity. So it's plus minus infinity. That means fields are free there. But that's just an assumption for the construction that I'm going to make now. So tau equals minus infinity. So if I take e to the minus, so e to the tau goes to e to the minus infinity. That means I am at the origin. So either I am at the very bottom of the cylinder, so all the way down on the cylinder, or I am indeed at the origin. I'm not sure if you can see this right, at the origin on the complex plane, right? So that's what that means. So we're going to go there now, and we're going to propose the following. We're going to propose the operator state correspondence. Operator state correspondence. And the operator state correspondence goes as follows. I can construct a state phi as the limit when z and z bar reach the origin of a field acting on the vacuum. And this thing is claimed to be in the Hilbert space. And we're going to see, so actually you see in the notes, well, I have you do an exercise, exercise 4.6 for free fields, bosons and fermions, where I just ask you to take a look of how that works. Free fields, check it out. Let's just say check it out. Check it out. We can have already sort of, for instance, if I take so at h equals h bar equals 0, we had the identity field. So let's just write the identity state, which is the limit of z and z bar going to 0 of just the identity field acting on 0. This, by the way, is something that I didn't write in the notes. I may add that. I'm just giving you an example since we talked about the identity field, but the identity doesn't do anything and there's no dependence on z and z bar. So we do have a state. So the identity field does indeed correspond to a state, and that's just the proposed vacuum state of the theory. This is an example. The other examples are the free fields, and we're going to talk a bit about an example in a minute. Well, not in a minute, maybe. We'll see as time is progressing. So, and likewise, you can define asymptotic out states. There are asymptotic out states, which I derive. So here I'm just going to tell you the results, and in the notes I actually give you a motivation for why this definition that I propose here is meaningful, and I derive it. And now I'm just going to make a check. So what we see, if you take a look at this, is, well, in a sense, we're having something very similar to here, where we just have the state evaluated, applied, sorry, the field phi applied to the vacuum state. And now I just Hermitian conjugate the vacuum state, that's this guy, obviously. And then I apply the same thing. I apply the field phi to it. How do I apply the field phi to the origin? Sorry, to the vacuum. Well, I have the coordinate z tend to the origin. So what is the counterpart of the origin? Well, by inversion, that's going to be infinity, the point at infinity. So that's this limit. And it turns out that if you just did that, you won't get something which gives a well-defined inner product. You need to include these two factors. Okay, let's see this. Let's see this. Check this. So check inner product. So the inner product between two fields phi1 and phi2 is going to be, and now I'm just going to plug in limit of z and z bar going to infinity, and zh1, oops, 2h1, z bar 2h1 bar, and then limits of w and w, maybe let's call the z1 and z1, and let's call these guys z2, so there's a 1 and a 1, z2 and z2 bar going to 0. I won't use w now because I just declared w as a coordinate on the cylinder and I don't want to confuse you. And then here, let's make it down here. So times, so there's the out state, the out vacuum, phi 1 of z1, z bar 1, phi 2 of z2, z bar 2, and this thing. But this thing is just a 2-point function. So I can just go and plug in the 2-point function. Let me do this here. So this is going to be d12 divided by z1 minus z2 2h1 delta h1 h2, and the same thing in the anti-holomorphic sector, z1 bar minus z2 bar 2h1 bar, and let's put the delta here like that. And now you can evaluate the limits, right? In the limit where you can just take the limit of z2 going to 0, that's not a problem. Z2 going to 0, you just get rid of this piece. And now you see where the necessity for these two guys comes from. The necessity comes from canceling the Z1 pieces. Otherwise, this thing just goes to, so if you evaluate the limit of Z1 going to infinity, this thing is just going to shrink to 0. Like the overlap is just going to shrink to 0. But if you include these additional factors, you just neatly get the normalization D12, D12 complex conjugate. Usually, like I said, they're just one, so they don't appear. And I should say, like, this thing is not meant necessarily to be the complex conjugate of the other, but that's not so important. It's just a minor detail now. And very importantly, you have the Kronecker deltas. H2 bar. And here's where you see the statement of orthogonality, right? So orthogonality. So that's the statement I made above that 2-point function, that two fields are in this sense, two fields can be thought of as orthogonal to each other. On a Hilbert space. All right. I'm going to make, just interrupt me if you do have a question eventually. I'm going to make I blacked out.
Yeah, you did.
I blacked out?
Yes.
How long did I black out? Damn it.
No so long ago. You were talking about the orthogonality.
Okay, so all that what I said there is that before I said that fields are orthogonal to each other, and I can only make this statement. The statement is made more precise because there's a relation between a field and a state. On a Hilbert space, I have a notion of an inner product, which gives me a notion of orthogonality, right? And because of that notion, I can now talk about fields being orthogonal because I have the operator state correspondence. That's all I said. Are there questions? Okay. Now I'm going to make a jump with respect to the nodes. I'm going to skip a bunch. So let me be very. So there is the section 5, which is about the Virasoro algebra. Virasoro algebra. So this is a deep dive into the Virasoro algebra. And we're going to use it now to construct Fock spaces. So here's where I do make the jump. So the first section Are you guys all forcefully muted?
Yes and no. We can talk.
Okay, cool. This looks like the internet's trying to kick me out. That's bad. Let's see. Let's just hope that doesn't happen again. And recording is still going. That's good. Okay, good luck. So the section 5.1 is what it is good for is, so I told you that the energy momentum tensor is a function, has two components, and for instance, the holomorphic component depends only on z. And in this first section, what I do is I show you that you can think of the energy momentum tensor as having a so-called Laurent expansion. Think of it as a Taylor expansion with negative powers included. Like Taylor expansions just have positive powers, right? But you can also, if you include negative powers, you have a Laurent expansion. And indeed, the LNs, I argue that the LNs, so in the notes, I argue that the LNs are indeed the modes which satisfy the Virasoro algebra with the central charge term, n squared minus 1. So this is what I do in the notes. So I'm just gonna dump this on you right now, and keep moving, because I want to talk about, in the remaining 15 minutes, talk about the structure of Hilbert space. And now I can. So here's I hope this is going to be comprehensible. So ask questions. So the aim here, so in 5.2, this is called Verma modules and conformal families. And the main takeaway that I hope for you guys from this section is really to understand what conformal family is. So these things are going to be the building blocks that we want to talk about. So at least I'm going to be using that a lot in next week. So the aim here is sort of structure of Hilbert space. Structure of Hilbert space. And it's going to be Fock-like. And let's just work a bit with what we already have. So we have global conformal invariance. Global conformal invariance demands the following. So we have a ground state, and this ground state, if the system is going to be symmetric, the ground state needs to reflect these symmetries. And this means that global conformal symmetry needs to be imposed on the vacuum state. What that means is that L0 and L plus minus 1 annihilate the vacuum. And likewise, L0 bar, L plus minus 1 bar. They also annihilate the vacuum. And this is sort of, so this is start. So from now on, I'm going to sort of ignore the anti-holomorphic sector and only talk about the holomorphic sector. And now there's a bit more. So let's make, so I want, for instance, there's more. There are more constraints. There are more constraints. And this is something where we can hope to make some, oh, there's somebody who wants to be admitted. Yeah, sure. And so let's take the energy momentum tensor and let's construct a state out of this. That means the state T, it's just going to be holomorphic, is T of Z applied to the vacuum state. Now, I just told you that I want to think of T of Z as a Laurent expansion. That means there is coordinates, an expansion coordinate Z, and then there are some Laurent modes Ln. And just as in free field theory, like sort of the Fourier components of a field, or in this case, the Laurent components of a field, they are going to be operators acting on Hilbert space. So they're being promoted to operators in Hilbert space. So that's what typically happens. So, so let's look at this. And we encounter a problem. So the limit when z goes to 0 for all positive powers, say when n is minus 100, so this z is z to the 89, so it has a positive power, then the limit of z going to 0 is not a problem. So the mode just disappears. However, the opposite case, where the power of z is negative, is problematic, because then this expression here is ill-defined, right? So what we're going to do in order to save this, or actually what you should do, it's not just what we're going to do, what you should do in order to save this, is that we find a constraint. So we demand that ln on 0 gives 0 for any n which is equal or bigger to -1. And if you do that, we can just evaluate t. So we just get the only one that remains, and you're invited to check that, is -2. And in this way, you see that you have a correspondence between a field T, right? So this is the field T, and it basically when acting on, so when you construct a state out of the field T, this is the state that you find, L-2 acting on 0. Okay. So that's what we find from here. And in the notes, there's a lot of technology that I developed in the notes, and I'm just going to give you the upshot of that. The idea is that now you can take a primary state, consider a primary state, consider a, or actually it's, yeah, consider a primary state. And what this is you take, let's call this phi. And as before, I'm going to restrict to holomorphic, so you can add an anti-holomorphic piece for yourself. So this just means that the field, oops, this is a primary field. So it has a very particular form of transformation under conformal symmetries, under conformal transformations. And what you can show, or what I show in the notes for you, is that so you act with L0 and it returns for you, it's sort of, the primary state is an eigenstate of L0 with eigenvalue H, which is its conformal weight. And moreover, Ln phi is 0, so this thing is annihilated for any positive n. And you can check that if you pick, obviously, if you pick H being 0, then sort of you revert to these conditions here. Oh, that's a bad box. So this is what we have for primary states. And let's see, what does the time say? Oh, 5 more minutes. Would you mind if I go like 5 minutes over time? We started a bit late.
It's fine.
Okay, all right. So whoever has to drop out, just drop out. I won't force you, but I'll just go a bit over time today. Okay, so now we talk about Virasoro modes with positive index, right? So they are going to be annihilators. So if Ln positive is annihilator, whoopsie, and damn it, annihilator, then Ln with negative index, so L0, we've seen L0 is sort of the diagonal one, so that one is neither annihilator nor creator. But the others here need to be creation modes, creators. And how do we see this? So now we introduce the notion, well, I already said this, sort of descendant states. And here I remind you of Fox spaces. So what we're going to do is we're really going to take we're going to take a Fox space approach where these LNs, or LKs in this case, are basically just Fock modes acting on a ground state. And the ground state is going to be the primary state. And these indices are positive, and there's a convention. So the K's are positive. Okay, and this is just a convention. We see that, for instance, L minus 2 acting on 0 is a descendant. So this is an example that we have encountered already. L minus 2 is a descendant. And now we can also evaluate the conformal weight, right? So let's call this here, let's not give it a name. So the conformal weight of descendant is read out by L0. Now we use the Virasoro algebra, so use that L0 and Ln, they have the following commutator. And then you can just find that a descendant has a conformal weight, which is just K1 plus K2 plus ... plus Kn plus the conformal weight of the primary state at the bottom, so the ground state that is being acted upon. So what you see is that all that you need to do is like one Virasoro mode, what it adds to the conformal weight is really just the negative, it's just the mode index. But so if you have L minus 2, you have a conformal weight of, if you have L minus K, you have a conformal weight of, you add a conformal weight of K. And this thing is called the level. So this is the level. And for instance, this is how we can read out the conformal weight of the energy momentum tensor, because T is just L minus 2 acting on 0. That means that the conformal weight of T is just 2 plus 0, because, well, 0 has no conformal dimension. Okay. So that's how we do that. And we can count. We can actually, like, given a, this is the last thing we're going to do now. This is like the last 5 minutes. So we can count the states. So all of the, like, the space spanned by a primary phi. And I'm not gonna say primary field or primary state. It's gonna be understood from context. And all of its descendants is called the Verma module. This is just a name. And the notion of a module is from representation theory, but for lack of time, I won't talk anything about that. So we can actually count states. Count states in the Verma module. At each level. So let's do that. I'm going to do a small table. So, well, it's not going to be super duper small, but so it's going to consume space, but it's not like it's going to have like a tremendous amount of information. So then there's going to be a basis vector at an energy level. For instance, so if I have an energy h phi, then there's going to be the primary field phi, and I can increment energy by 1 if I act with L minus 1. So L minus 1 on phi, and that's the only way I can increment energy by 1. For instance, energy 2 increment, there I have two choices. I can take L minus 2 squared, but I can also take just straightforward L minus 2. And for in a minute, I'm just going to tell you that this is sort of 1 plus 1 and 2. I'm just going to write this down. 1 plus 1 being L minus 1 squared. So it's 1 plus 1. And the next step, I can take h phi plus 3. And there I have more options. I have 3, right? I can take L minus 1 cubed. I can take L minus 1, L minus 2 phi. And I can take L minus 3 phi. Let me make separate another column at the very end. And here we're just going to count the number of states. So here we have 1 state. Here we have 1 state. Here we have 2 states. Here we have 3 states. As before, this is 1 plus 1 plus 1. This is 1 plus 2. And this is just 3. And let's do another level, h phi plus 4. That's L minus 1 quartic, L minus 1 squared, L minus 2 phi. Then there is L minus 2 squared phi. And L minus 1, L minus 3 phi. Let's make a bit more room. And finally, L minus 4 phi. And this is 1 plus 1 plus 1 plus 1. This is 1 plus 1 plus 2. This is 2 plus 2. This is 1 plus 3. And this is 4. And these are 5 options. Okay, so let's make this a bit smaller. Okay, so you see, so why did I make these orange numbers? The reason is that I want to tell you that the number of states at each level goes with the partitions of an integer n. So if I call sort of the level n, so h phi plus n, then I'm going to have the partitions of n. What are the partitions of n? So if I give you an integer 2, right, then I'm just asking you, what are the options that you have to write 2 as a sum, as a positive sum of integers which are either 2 or smaller? Well, that's just 1 plus 1 and 2. These are just 2 options. For 4, if I have level 4, then I have 5 options, which are 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, and so on, the options that you see here. So if I really want to count at each level, that's the last thing, so now I'm really running over time. So to count states, introduce a bookkeeping device. A bookkeeping device, and this is just going to be Q, that's just going to be some complex number, but it's not going to be so important for now. For now, we can just conclude with states are being counted by so it's just going to be the sum of n from 0 to infinity, the partitions of n q to the n. What is this? This is 1 q to the 0. That's just when n is 0, I just have this 1. Then I have 1 q to the 1 plus 2 q squared plus 3q cubed plus 5q quartic, and so on. And just as a last remark, this can be resummed into this. All right. Long story short, at the end of the day, this is the structure of the Hilbert space that we're dealing with. So we're having basically a Fock space. That's it. So you see that you have sort of these guys. You have a primary state that's sort of like the ground block. That's the primary state, and you're going to construct the Fock space with the Virasoro modes on top. That's the structure of Hilbert space. And in essence, if you want to conclude today's lecture with the sentence is to say that in QFT, usually you have an infinite number of states. Hilbert spaces are infinite dimensional. And in CFT, that's no different. You have an infinite number of states because you have an infinite number of Fock space elements. But here it turns out that all that you need to do is you need to find primary states, and there are going to be several. For instance, in the Ising model, they're going to be 3. And all that you need to do is find these primary states, and then you can organize all the infinity of states that comes afterward as descendants of these primary states. And that's it. And tomorrow I'm going to be a bit more clear on how to think about, or I'm going to repeat that. So sorry for going over time. Are there questions?
Yes, if you may. So is it called a modular for a mathematical reason?
Yes, it's in representation theory. What we do is you take a group, or you take any abstract set of rules, for instance, a group, and you map that into operations on a vector space, right? And that vector space, in physics, we just call both things so we call the vector space a representation, but in mathematics, it's called a module. And it's the same here. It's a module. Was that helpful?
Yeah, thank you.
Other questions? Yeah, the person who asked about the structure of Hilbert space, is this a bit clearer now, how the structure of Hilbert space is to be understood now? Yeah, maybe it's already gone.
It's clearer now, thanks.
Okay, cool. All right. So how do I stop the recording and then there can be more? Here, pause, stop recording. Stop recording. I'm going to stop the recording now, and whoever has more questions can stick around, and we'll just see how long this goes. Do you want to stop cloud recording? If yes, you receive. uh,